Good morning, everyone, and welcome to the third day of the workshop, or third half a day of the workshop. The first speaker today is Urvashi Oswal from University of Wisconsin-Madison, and she'll be talking about selection and clustering of correlated variables using GrOWL regularizers.
Thanks, Mariam. Like Mariam said, I'm a PhD student at UW-Madison, and Rob Nowak is my advisor. So today I'll be talking about mostly work that Rob and Mario have developed over the last 2 years, and I'll also talk about some of the extensions and applications that I've worked on very briefly. So let's begin with the usual linear regression setup. So we have y is equal to x beta star plus some noise. So y we have n measurements of an unknown parameter vector beta star through rows of x, and we're in the high dimensional setting where n is or the number of measurements is smaller than the number of parameters. And we're also assuming sparsity, so a lot of the elements or entries of beta star are 0. In other words, a lot of the columns of x do not really contribute to the measurements y. And our goal is to estimate beta star, the unknown parameter vector, from y and x. The motivation, that the application that we started working on in this problem was where each of these entries of x are measurements of activity in the brain, different brain regions. So a column would correspond to a region in the brain, and we're measuring measurements. We're measuring the activations in the brain in response to stimulus. So what we saw is if you go to a really small fine granularity in the brain regions, you see a lot of correlations in the activations in different brain regions, because we are basically measuring the blood oxygen, the flow of blood oxygen through the brain. So if you were to go very, if you look at very close by regions in the brain, you would see that a lot of these columns of x are very correlated. So we are in that setup. So that's the setting. And we have the usual classical estimators, the ridge and the lasso. So just to give a review, what ridge and lasso are saying is that we want to find a beta. Let's say we are in the two-dimensional setting where we just have two variables, two columns of x. We want to find beta such that the 2 norm of that beta is small, so it lies in this ball, and it also fits well to the data. So the best fit to the data would be just the least square solution, and how far you go from the least square solution is shown by these contours. So the solution to the ridge optimization would lie somewhere at the intersection of these contours and the the L2 ball, which is this point in this case. And in the lasso case, we have a similar data fitting term, so the least square solution and the contours. And as you go far from the least square solution, and at this point, this is the L1 ball, you would intersect at this point, which is the property of the L1 ball, that it's this pointy, it has this pointy shape here, which is basically saying that beta 1 would be set to 0. So you get these sparse solutions. And because of the sparsity in the lasso solutions, you can use it for feature selection. So you can say, look at the columns of x, or the features that are variables that got the most, got a non-zero weight, and get a variable selection out of it. So that's great. That's what we want to do, right? We want to find regions in the brain that are relevant to a certain task, or the process a certain kind of information. But the problem is that if we have a lot of highly correlated variables, Lasso selects only a subset of them. Just to show an example, this is just a toy example where we have a matrix X with groups of 3 identical columns. And let's say there's a beta star that's generating the y measurements, but it doesn't have to be this specific beta star. Some beta star is generating y, and then we fit a Lasso solution to it. What Lasso does is that it will pick only one column out of these groups of identical features and leave out the rest. Because Lasso is looking for sparse solutions, it doesn't make sense to get redundant information through these identical columns, so it just says, let me take one of them and then let me find another one that gives me more information. But this is a problem if you're dealing with, if you're in this setting where you want to find all the brain regions that are processing some information. You don't want to leave out certain brain regions that might be corresponding to these columns that have correlated features. And for the sake of interpretability, we want all the covariates that are relevant to some task. So that's the goal. One way to fix this problem would be that if you knew a priori which groups were, which features were grouped together by their correlations, you could just use some kind of group sparsity. But the problem here is that we don't have this group structure. There's been a lot of different work dealing with correlation. I won't go into a lot of details, but we look at ElasticNet and Oscar in the next slide, so I'll just skip them for now. Marginal regression, basically they look at all the variables or features separately. They're regressing over each variable separately, so they don't really get affected by correlations. Stability selection, basically they just run a lot of different Lasso problems over different random subsets of the data, and then you can hope to get all of the relevant features through that process. Cluster Lasso, basically they have this two-stage method where in the first stage you try to find all the correlated groups of correlated variables, cluster them based on correlations, and then you run Lasso on some subset of that problem. And I'll come back to Oscar and ElasticNet, but basically most of these methods have just some asymptotic consistency results, and they don't always perform better than Lasso. They sometimes show improvements. And there's this Oscar method, which I'll describe in a minute, but basically they have a lot of different experiments showing that they beat the state of the art. That's why we got interested in this problem. And here's the ElasticNet and the Oscar optimization problem. So you can see the ElasticNet is just the Lasso plus an L2 penalty. So basically what they're doing, so here we have the Lasso ball as before. This is beta 1, beta 2, and this is the L1 ball. If you add an L2, you get this green curve, which is basically adding some smooth, or if you were to take an elastic band and put over the L1, you would get this smoothed L1 plus L2 regularizer. So that's the point of the ElasticNet. That's the structure of the ElasticNet. And this Oscar is also a variant of the L1 plus some pairwise so that they're doing L infinity over pairs of variables, two groups of two variables. So if we have only in this setting where we have just beta 1 and beta 2, this max is just the L infinity now. So you have the L infinity ball looks like this, right? And then the L1 plus L infinity gives you this Oscar octagonal shaped ball. So it has the usual L1 points, the sparse points where beta 1 or beta 2 is 0. And it also has this additional point where beta 1 is equal to beta 2. Those are the points that minimize the L infinity now. It's much more complicated, but in the two-dimensional setting, it's just the sum of L1 and L infinity. And the difference between the ElasticNet or let's look at these two at the top. So basically, what I'm showing here, this is again the least square solution, the beta LS. Depending on how correlated x1 and x2 are, the two columns of x, you get either these circular contours. So if they're not too correlated, if they're not very correlated, if they're independent, you get these circular contours. And if they're very correlated, then you get these elliptical contours. So what happens is, if they're not very correlated, you tend to select the, Oscar tends to select the Lasso L1 solution, so it gets you the sparse solution. And if they're very correlated, these elliptical contours, they would tend to intersect with this point where beta 1 is equal to beta 2. So what this is giving you, what this is giving us is that correlated variables get identical coefficients, exactly equal coefficients in the solutions of the Oscar optimization. Okay? And it's competitive in terms of the error, and like we see here, I should also mention that elastic net wouldn't have the same property because it has this smooth curve here, so it would pick both beta 1 and beta 2, give them non-zero values, but it wouldn't give them exact, it wouldn't yield exact coefficients in the beta vectors. It would give some, you cannot look back at the beta and say that these were grouped together. So that's what I mean by explicit variable grouping here. Okay. So just to go back to the toy example and see what happens in the case where we have identical columns. Again, beta star is something, and then the Lasso solution is this sparse solution. But then Oscar, if I was to solve Oscar instead, it gives me this explicit clustering of these identical groups of identical columns. Yeah, exactly. So now we're going to generalize the Oscar to an OWL norm, which is the ordered weighted L1. I don't know if I say it here. Oh, the ordered weighted L1. But basically, let's start by looking at the Oscar just for a minute. We have the L1 plus these pairwise maxes. It turns out that you can rewrite this as the sum over weighted sum over the magnitudes of beta I, such that you weight them in a certain way that depends on the magnitudes of the beta I. So if you sorted the beta coefficients, the largest coefficient would get the largest weight, and then you keep linearly decreasing the weights that you give them, and you sum over them. That's the Oscar. And the generalized version, OWL, is just an ordered weighted L1 where you can have any set of weights that satisfy this constraint. So they don't have to be linearly decreasing, but they're still non-increasing. And you weight the magnitudes of beta I depending on their how big they are, and then sum over them. So that's the ordered weighted L1. And this is you might have also seen it as being called as slope. Candice and Bogdan have this paper where they look at the same regularizer in the sense of false discovery rate and not with strongly correlated covariates. So we are going to focus on this specific problem. Here I'm just showing, if you're familiar with the atomic formulation of the OWL norm. This is in this paper they show that the OWL norm has these atoms, basically the same as the L1 plus the union of the L infinity atoms. And this is just a three-dimensional view of the same OWL norm. And in the same paper they also show that the proximity operator can be computed in P log P computation, so you don't really pay more for this ordering and weighting. And you can do it really quickly. And you can use proximal gradient descent to really solve the OWL optimization. That's all I'm going to say about it for now. If you're interested, you can look at the paper. And the GrOWL norm is just a group version for multitask regression. I'll come back to this problem where we came up with it, but basically by multitask regression I mean that instead of just one linear regression problem, we have R linear regression problems. So we have R vectors of y, and these regression problems all share the same features x, and they probably have the same support as well. So the betas have the same support. So y is equal to xb, you can write it as this matrix problem, and then you can say that B is row sparse. And to solve this problem, you can just use group Lasso. Say that the L2 norm, so you can try to make a lot of the rows of the L2 norm of the rows of B's to be 0 to get a row sparse solution. That's all this is saying. But we again face the same problem here. So if the columns of X were very correlated, then group Lasso would not pick all of the variables, and it would just pick a subset of them. Here I'm just showing another toy example where I generate an X with very correlated features. The columns of the 5th and 7th columns of X are very correlated. And this is the group Lasso solution. You can see that group Lasso picked the 5th feature and just left out the 7th one. Whereas GrOWL, which I'll define in the next slide, picked both of them and gave them, like the OWL, it gives them similar weights. I'll talk about the exact clustering result in a bit, but basically the L2 norm of these two are exactly equal. Rows are exactly equal and they're very correlated. So here's the GrOWL norm. It's just weighted, again ordered, weighted, but now we are ordering the two norms of the rows of the matrix B based on their magnitude, and then we're weighting them similar to the OWL norm. Okay, if you just have one linear regression problem, this just becomes the OWL norm. Okay, so we've defined. Was there a question? So we've defined the OWL and the GrOWL norm, and now we're going to look at the clustering properties of these. I've stated that they cluster correlated variables, but how exactly is what we'll see next. But before that, just let's look at the special cases of the OWL norm. So this is the OWL norm in the two-dimensional case, where we just have beta 1 and beta 2. We weight the bigger of beta 1 and beta 2 by W1, which is greater than W2, and then we weight the minimum by W2, and we sum them. So let's look at the case 1 where W1 is equal to W2. So if you just had no difference in W1 and W2, you get back the L1. This is just the L1. And if you set W1 to be something greater than 0 and W2 to be exactly 0, then you get the L infinity. So those are the two extreme cases of the OWL solution, OWL norm, and if you set anything in between, you get this octagonal shape. The point to take away from here basically is that this gap in the weights W1 and W2, the difference, is kind of influencing the clustering, because if this gap was 0, then you don't get any clustering, so you just get the L1. And if this gap was made the maximum, then you get clustering always, regardless of how correlated your variables are. And which is what we prove in this theorem. So we're back in the linear regression setup now, where we have this y vector x beta hat, which is the solution of the OWL norm, OWL optimization. And we prove that if xi and xj, a pair of columns from x, are close in the L2 distance with some function of the delta, where delta is defined as this now, generalized, the min of overall the gaps in the consecutive weights of the OWL norm. But if they're close, if the xi and xj are close in the L2 norm, then beta I hat is equal to beta j hat in the solution of the OWL optimization. Okay. And there's also another version where they don't have to. So basically, if they're correlated, xi and xj are correlated in some sense. They get exactly equal weights, coefficients in their OWL optimization solution. And this recovers the clustering theorem from Oscar under less restrictive assumptions, and it's also proof for, instead of L2 here, if you had the L1 loss, you can also prove the same thing. So I'm just gonna, before I go there, are there any questions? So just to prove this theorem very quickly, let's look at the very simple case where beta is just again two-dimensional, and we have just positive beta 1 and beta 2, and beta 1 is greater than beta 2. Let's just say that we are in this very simple case, and we define a Robin Hood transfer of size epsilon as V, where V1 is beta 1 minus epsilon and V2 is beta 2 plus epsilon. Basically, why it's called the Robin Hood transfer is that they use this in the economic inequality to measure economic inequality. Basically, what it's doing is it's saying take from the rich and give to the poor, so that you have equality. It's easy. You can do the computations, and it's easy to see that the OWL norm of this new transferred vector V is actually less than this. The OWL norm of the original beta. Basically, what we can prove is that the OWL favors these flatter, more uniform vectors over non-flat coefficient vectors. Of course, there's a lot more going on here. It's just the two-dimensional case, and there's just positive betas, but you can generalize this using some tools from majorization and shear convexity, and you can show that OWL favors these flatter vectors over beta. And to complete the proof, you can show that this the objective of the OWL optimization for this V vector is smaller than for if you assume that beta was your solution and you did not have equality here, then you can show it by contradiction that this is actually smaller. I might skip that here, but let's see. So you can so basically showing this is equivalent to showing this, and we can show that the L2, the least squares optimization is bounded by this, and then just take my word for it for now. But then using this a general version of this OWL property, you can show that this is less than or equal to this, which, that's another property. This is from the assumption that we had in the theorem that xi and xj are closed in the L2 norm. And you get this, and then you can use the property of this OWL norm here to get that the OWL optimization of this vector V is less than the OWL optimization of beta. So basically, this should be the solution and not this. And that completes the proof. We also have similar theorem for the clustering properties of GrOWL. Now we have, instead of just a vector y, we have a matrix y and the matrix B. What we can show is that if B hat is the solution of this GrOWL optimization, then, and if xi and xj, the columns xi and xj are identical, then the rows beta I and beta j hat corresponding to these columns are also equal. And also, if these, again, it's the same thing, if xi and xj are close in the L2 distance with some function of this gap delta, then the 2 norm of these beta vectors rows is also equal. And additionally, we can show that if depending on how close these xi and xj's are, the columns are, the rows of the solution vector, the solution matrix are also, the corresponding rows of the solution matrix are also close, very correlated. Okay, so that was the properties, clustering properties of OWL and GrOWL. Let's move on to the error analysis. So we have this observation model where y is equal. Let's just focus on the linear regression setup where we're using OWL. So y is equal to x beta star is s sparse, and the noise is bounded by some epsilon in L1. That's all we assume. And let's say the rows of x are generated using this Gaussian model where the variance is C transpose C. So another way of looking at that is, say, x can be written as B times C, the product of matrix B and C, where B is just IID Gaussian with unit variance, identity variance, and C captures most of the correlations in the x columns of x. So it's the product of this IID Gaussian matrix times this C, which is telling you which of the columns in X are correlated or identical in this case. And you can also do the same for X not having identical columns. Just C here wouldn't be like exact zeros here, but basically you would get correlated columns. And here also it's showing you what columns of X are correlated. So this is just showing you how C transpose C would look. So you get this nice block structure in your covariance matrix. So what can be shown about the OWL solution optimization problem is, this is a slightly different way of writing the OWL optimization. So you're minimizing the OWL norm subject to the least squares solution, the L2 norm being small, error being small. And if you write it this way, then you can show that the distance between the solution beta hat of this OWL optimization to the true beta star in some weighted distance, L2 distance sense, is smaller than this, where what is important is that you get this S log P dependence, which you get with Lasso. So the S is the sparsity of beta star and P is the dimension, and then if you have more than S log P samples, you can get close to the true beta star in this weighted sense. Yep.
What's W bar?
All right, maybe I did not mention it here. W bar is just the average of the W's. So there's some constants depending on the OWL norm. This is usually pretty small, and the rest are just constants. And the proof is based on some techniques by Versionen. Basically, they're defining Gaussian widths for correlated variables, and it recovers. So if C was just the identity, then you don't have any correlations in the X matrix. You just get back. And if OWL was just the Lasso, then this would also become 1, and you recover the known bounds for Lasso.
Don't you have the normal data proportional to square root of n? Since you get S over square root of n?
I think we assumed that. Maybe I did not mention it here, but I think the norm is more like 1. So the L1 norm would be more like square root of S, right? If beta star was, so the norm of the L2 norm of beta star is less than or equal to 1, then the norm of the L1 norm of beta star would be something like square root S.
The coefficients are all time then. Does that make sense?
Can you speak up, please?
Yes, of course. I'm just saying that this L2 norm of beta star is typically proportional to square root of S. I mean, it could be smaller, but then you make assumptions on the size of the coefficients. So this bounds reads to me like S over root n. But that's just my confusion, so we can talk about it later.
Yeah, I think we should take it out offline. But I think usually there is this dependence.
Lasso doesn't have that dependence.
Yeah, probably. Okay.
That is not one.
It's not one.
Wow.
So just for the special case where you have identical columns, so X has replicated identical columns and beta star is group sparse. You can show that this actually you can get rid of the C because beta star has this special structure which looks similar to beta hat, right? This is beta star, sorry, and you can show that beta hat is close to beta star with the usual. There's no beta L2 norm of beta star, but I think we assume that beta star is the L2 norm is less than or equal to 1 or something.
Do you assume that the noise is deterministic?
Sorry?
There was assumption on the noise. Assumption on the noise.
Oh, the noise assumption is on this slide. So it's just assumed that it's bounded in DL1.
This is the same epsilon which is in the definition.
Yeah. Oh no, I guess. Yeah, it is the same, I think. But there's also an epsilon here, so we are assuming that
different epsilon or it's the same epsilon?
Sorry?
It is a different epsilon or the same?
I think it's the same, but we're just assuming that we know this epsilon and then we're using it as the parameter of the optimization. So yeah, this you get this log P dependence, and then basically if you would Lasso or something, they would have to assume that you have RIP or like some restricted isometry property, which we don't assume here at all, right? This identical columns, you cannot assume that, and then you still get this S log P dependence, but you have some other parameters, I guess. So you don't pay any price for these collinearities in X using the OWL optimization. I guess I should say, I mean, so this C here is saying that we get a superset of the support and not you don't get, if beta star was something else, you don't exactly get the support of the support of beta star, right? So that's how we get rid of the requirement that the matrix should be RIP. Okay, so in the last 10 minutes, I just want to go over some of the places where we use this OWL norm. The first one is just the one that I mentioned, the brain imaging problem, where we needed better interpretability of the solutions. And then there's some work that we've recently done in subspace clustering and deep learning. Mario has a paper on this, which use OWL to scale the solution. So just a review of what I said in the beginning. We have a person in this fMRI scanner. We measured the activity in different regions of their brain in correspondence to some stimulus. So each row corresponds to a stimulus. Let's say they're images of some objects, and the columns of X correspond to some regions in the brain, which I'll just call voxels from now on. And we have like 100 stimulus items, so 100 rows. X is 100 by say 10,000 voxels. We got rid of a lot of the voxels in some pre-processing step. And like I said, there are some of the voxels in the brain have very correlated activation patterns. And the goal here is to say which of these voxels or columns of X are involved in processing some certain kind of information about the stimulus, which we are encoding as this labels. Actually, not labels. We looked at a different kind of problem, where instead of just the labels, we have some pairwise similarities among these stimuli. And this is the problem that Tim and Chris came to us with. They're in the Department of Psychology. And the question they asked us is, if we have this pairwise similarity matrix between these pairs of these stimuli, and this feature matrix where we measure the fMRI response of the person, can we find regions in the brain that together are most predictive of these pairwise similarities? So basically we have this S matrix which is symmetric and n by n. We have an n by p fMRI matrix, and we want to find a W, a weight matrix that fits X transpose to this similarity matrix. So which voxels, the correlations in which voxels represent this similarity matrix the most? And that's the question we are trying to answer. And we just solve it using this hack where we say, I'm assuming PSD for here, but we also have a technique for non-PSD matrices. We can say that X is equal to Y transpose, and let's say W is also a low rank. We have reasons to believe that W is low rank because of the way the brain is structured. We can say that this is BB transpose, and let's solve the problem, the square root version, where we just fit a B to X that gives us Y. So we have the multitask regression setup that we saw, where we try to solve Y is equal to XB instead of this similarity version. And a lot of these rows of B correspond to the voxels in the brain, so we want B to be row sparse. And we apply group Lasso, and we also apply GrOWL to this problem, to this data, and we showed that basically in a very simple toy example where most of the people from psychology agree on the solutions, that this visual similarity structure, that the voxels that GrOWL and group Lasso find are pretty much in the regions where we would expect them to, so the back of the brain. And you get more stable selections with GrOWL than group Lasso, is what we showed in this paper. And as part of, Chris has graduated now, and he's at Manchester, postdoc at Manchester. As part of his thesis, he also applied GrOWL to a more controversial set of similarity structure, the semantic structure, where if you wouldn't have done GrOWL, you would not see certain regions in the brain in the group Lasso solution. So GrOWL finds those regions, and he was trying to show that because of the correlations in these regions, group Lasso would have missed them, but GrOWL picked on them, and that those regions are also involved in processing this semantic information. I don't have those results here, but that's basically what we did with that data. And just very quickly, subspace clustering, if you have seen that before, you just have you're given a set of data points from a union of subspaces, something like this, and you're trying to cluster the points into distinct subspaces based on their subspaces, and you don't know these subspaces, obviously. And if you've seen this before, you know that people use sparse subspace clustering, which is basically saying that you want to represent each data point as a sparse linear combination of the remaining data points. So they use some kind of L1 minimization, and the idea is that usually if you picked a data point and say this S1 subspace, only points from the Lasso solution would pick points from the same subspace. And that way you can find a clustering based on that solution. And what we observed is that usually points in the same subspace would tend to be more correlated than points in the other subspaces, so we could probably use OWL here and get better solutions. So here all I'm showing is like each column of this adjacency matrix is just a solution of the Lasso on one of the data points. And we see that with Lasso you get much fewer points selected from the same subspace than with OWL. I'm skipping over a lot of the details here, but this is the basic idea that we were hoping to see. And we see that you can use the basic goal is that we could probably use fewer OWL optimizations, run fewer OWL optimizations, and do this very quickly, because here you need to do, like, if you have n data points, you need to do n Lasso computations, which is pretty expensive. I'm going to skip over those things, and then just to mention very quickly, there's a third application that people, that Mario and Laura Bolzano have submitted to ICLR. People usually try to take something like Lasso and group Lasso to find subsets of these neurons in the deep neural networks that can be thrown away, are redundant to the problem. And that's basically what they're doing here. So they're saying that these red ones are not really required in this problem, so you can throw them away. And then they can, using GrOWL, they can find that these blue ones are actually pretty correlated and redundant. So you can share or tie their parameters in this in these two blue ones to generate an even compressible, smaller network. So that was the basic idea here, is to use GrOWL to eliminate unimportant neurons and identify strongly correlated ones to compress the network. So just to conclude, the one takeaway from this talk would be that OWL automatically clusters correlated variables and assigns equal coefficients to them. What I mean here is that I'm just trying to say, if you were to think of these correlated features or columns as noisy measurements of the same feature, so you can think of these voxel measurements as noisy measurements of the same signal, then giving them equal coefficients is equivalent to averaging them or denoising them in that sense. And here are some references, and thank you for your attention.
Any questions?
Regarding your last slide, actually, where you explained nicely what it does. Suppose you have a group of variables where just one is, say, biologically relevant. You have a large coefficient and the others are 0.
Mm-hmm.
Would then your method not be so ideal or so good? Because it's kind of like a sparse alternative, right?
Yeah.
And this is kind of more like a dense averaging effect, what it does. Is that?
Yeah. So
Have you tried it out to see?
So that's what in some of the slides I was mentioning, that beta star could be sparser than what OWL picks, but then I guess the goal is that you want to find a superset and not miss any relevant ones. So we really care about finding all the relevant ones, even though it might pick some of the irrelevant ones in the process.
Yeah, but the superset, suppose there's a set of two variables. One has a large
Actually, that's a great.
The other one is 0, and what that does,
That's actually a very
kind of
good
averaging
point.
out on a half, right? One is 1, one is 0, and then
Yeah, that's a good point. So if, but basically, what all I'm trying to say is, let's say we're in the extreme case where all of the variables are identical. There is no way to look back and say that this was the relevant one, right? All of them have the same signal, so there is no way to look back and say that this was the right one. So the best thing to do there is to just pick all of them, because they're all containing the same information.
the question is somehow whether you can find the group better by having some sort of a more sparsely oriented technique than averaging.
Yeah,
But it's
I get what you're saying, but I think that it's not possible because of the if they're exactly identical, there's no way to look back and say.
Well,
Yes,
that's,
well.
we can talk offline about this.
Yeah, well.
No, go ahead.
You had some results where you show some easy to check conditions to determine if two variables, pairs of variables can cluster together.
Mm-hmm.
So can you, in those cases, can you just merge those columns, either by averaging or subtracting, to reduce the computation?
I guess those are just sufficient conditions, but OWL is doing a lot more than that we
Right,
don't really
okay.
have. Yeah, I guess we could do that if we knew, upfront. That's a good point.
So
well, maybe I missed it, but so this norm, we have the weights that define the norm. So what choice of the weights do you use for the results?
Yeah, so we use a bunch of different weights. I skipped over that, I guess. And like what we ended up choosing in the end is something that looks like this. So you have a linearly decaying like the Oscar, but then it becomes flat like the L1. So a combination of like a linearly decaying weights set and then L1. But then, yeah, there's this question of how do you really choose the weights, the parameters.
You do grouping only for the strong coefficients,
Yeah.
and then
So
as it's just Lasso-like.
Yeah, that's what we find is the best thing to do, because if you were to just decrease the Oscar, like just keep decreasing, then you're constrained how much this gap between the two weights can be, and then then you just don't get any clustering.
Questions? Yes.
I know you're doing much more than this, but exactly, again, going back to your last slide and your explanation comes with it. You said that if you were to cluster according to the principles, you are clustering saying according to the size of the coefficients relative to a y, right? But say that you are to cluster the way, but you have kind of two ways of thinking about this cluster that kind of be combined together. So if you stay with one way that you didn't present, which would be what you said, however, on the last slide, that which that they have variables that are slight variations of the same thing. Say that if there was a method to cluster the x's independently of y, then you take averages. I'm just trying to push this idea to the limit, and then fit y on that. Have you done these kind of things?
Yes, we haven't done it, but in the very, very beginning when I said, yeah, so cluster Lasso.
No, I know. But the cluster Lasso of Peter here didn't. I mean, it's kind of doing that, but
Yeah.
you know, it's not exactly doing that. That's I think. Okay, well, we can talk offline. So
Okay.
that's
Yeah, it's not
comparison.
exactly the
Okay,
same,
okay.
but we haven't tried the other.
Okay, well, I'll
Okay.
Let's thank Urvashi again.